Okay, so we're gonna go ahead and go on to the next topic in carbohydrates, which is stereochemistry. I'm gonna step back in this video and kind of talk about stereochemistry a little bit. So, stereochemistry is basically the way that different atoms are arranged in a particular molecule. So, compounds that have the same chemical formula, they only differ in the way that their groups are attached. They don't necessarily have different chemical formula. Two stereoisomers of glucose will have the exact same number of carbons, exact same number of hydrogens and oxygens, but they'll only differ in their kind of arrangement, to say. So like I said, they differ in terms of spatial arrangement of component atoms. So in this video, I'm going to talk about enantiomers, and then the next video, I'll talk about diastereomers a little bit. So what enantiomers are non-identical, non-superimposable mirror images. And when I mean by non-superimposable, I mean that you can't put them on top of each other and have them line up exactly the same. Some group is going to be out of line. So that's what I mean when I say non-superimposable. So a chiral carbon, enantiomers, you can only have an enantiomer if you have a chiral carbon. So what is a chiral carbon? A chiral carbon is basically a carbon that has 4 different groups attached to it, and there is no internal plane of symmetry. To give you guys a little example, I drew out a random molecule that I don't even know if really exists anywhere, but I just drew this out to give you an example. So the first one over here, you can see that you have a central carbon that's attached to an OH group, a carboxylic acid group, a CH3 group, and an H, or a hydrogen. This carbon right here would be considered chiral because it has 4 different groups. It has 4 different groups attached to it. This one over here on the other hand, would not be considered a chiral carbon because you have a carbon with 2 hydrogens attached to it, and that doesn't fall into our definition of what a chiral carbon is. So that's a little background on what a chiral carbon is. You'll make sure you know how to do these because these really help. Identifying the number of chiral carbons really helps you determine how many stereoisomers you can form, and I will give you a formula for that in a little bit, but it really helps you identify the number of possible stereoisomers a particular compound can have, and that could probably help you on a multiple choice test where your professor or where your teacher might ask you how many stereoisomers can the following compound form. So to give you an example of an enantiomer, I can draw this over here, and to give you a little more detail about it, if you would look at the last OH group on top of the CH2OH, if it's on the right side, you're naming it as that dextro or D, and if it's on the left side, you're going to name it as L, which is levo. I'm not exactly sure in what language that means, left or right. I think it's Greek or Latin. But it's left. L means levo, which basically means that the last OH group is on the left, and then dextro is on the D. This is also the D and L kind of just mean what way the molecule will rotate plane polarized light. If it rotates it to the right, it's going to be D, and if it rotates it towards the left, it's going to be L. So you can't really determine that unless you have an experiment going on. You can't just look at a molecule and say, oh, it's going to be L. I mean, you can't just look at something that says R and say, okay, R, it means it's right, so let's say it's going to be D as well. You really have to do an experiment to figure that part out, and you have to go from there. And I'll get into a little bit more detail about R and S in the next video. So to determine the number of stereoisomers, what you do is use this formula where it's 2 to the n, where n is the number of chiral carbons. So you would just simply count the number of chiral carbons in a given molecule and put that to the make that the n and do the fact and do the exponent form, and it'll give you the number of stereoisomers. Another example for enantiomers, I kind of drew it down here. This is glucose, so let me write that down real quick. This is a glucose molecule. The original formula is C6H12O6, I think. So let me count. 1, 2, 3, 4, 5, 6. Yes, so it's C6H12O6. That's the formula. So you can see that almost every other OH is on the opposite side. So they're non-superimposable and they're non-identical, so that would make them enantiomers. Once again, you see the OH over here is, and this little dashed line over here is the mirror. So if you were to see a mirror image of it, you would see that you have the OH group on the right here, but you would have OH group on the left. So if you tried to put these on top of each other, they would not line up, which would make these enantiomers. Enantiomers differ at every single chiral carbon, or every single chiral center, and they kind of also reverse the stereochemistry. So if this were to be R, then if this little chiral center over here were to be R, then this chiral center would be S over here, and so it would flip each and every configuration at every chiral center. And that's that for enantiomers. In the next video, I'm going to talk a little bit more about diastereomers.